Okay, hi. So when Andres just warned you about his Latino accent, now you have the chance to hear a very thick German accent. So I'm happy to be here today and talk to you about stateless clients. So let's start with something that we all can agree on. Ethereum is trustless, right? Except for the part where we actually use it. So because most applications just ask an RPC, hey, what's my balance? And when you get an answer, they say, cool, I trust you. But that's not cryptography. That's hopium. Now, here's the problem. Your application is not trustless, even though Ethereum is, because most apps do not interact with Ethereum directly. They don't run a full node. They don't verify everything themselves. Instead, they ask someone else. They ask an RPC endpoint. Every time your wallet shows a balance, every time your dApp shows contract state, every time you simulate your transaction, it is asking an external service for the answer. And then it just accepts the answer. No verification, no proof, just trust. So while Ethereum is trustless, your app is not. It's trusting its data source. Every interaction on Ethereum starts with reading data. Before anything happens, the application asks questions. What's my balance? What's the current state of a contract? What will happen if I execute this transaction? These are constant reads. And all of these reads go through the same path, through RPC. So that's the data pipeline, dApp, RPC, Ethereum. And this pipeline is used all of the time, not just occasionally, continuously. Every screen you see, every number you rely on, every simulation you trust comes through this pipeline. And the critical point is the pipeline is outside the trustless guarantees of Ethereum. It sits on top of it, and it is trusted. Your entire interaction with Ethereum depends on this pipeline. Everything you see is just a response. So what does that mean for the security perspective? If your application trusts this pipeline, that pipeline becomes your attack surface. And the attacker does not need to break Ethereum or hack consensus or break cryptography. They only need to control the data that your application receives. Just lie a little bit, politely, through an API. For example, they can return a manipulated balance. They can change the result of a transaction simulation. They can hide transactions or invent ones that never happened. They can return stale data, so your application acts on an outdated state. Here's the problem. The application cannot detect this on its own because it has no way to verify the data. From the user's perspective, everything is wonderful. The UI looks normal, the numbers are perfect, but the decision is based on false information. And once the user signs a transaction, the damage is already done. You don't need to break the system, you just need to control what the user sees. So our natural reaction would be, let's just fix it. Why don't we just verify the data? We already know how to do that, but the existing approaches that we have don't work in practice. So let's look at them. We have full nodes. A full node verifies everything locally. So just by raise of hand, who of you runs his own node, his own full node? Very good. Not too many people, though. Now, of those who run the full node, do all of the applications that you use actually rely on the data of your node? Probably not. So even though the full node is the gold standard, your apps still run on the data they receive, probably from some kind of centralized service. And full nodes themselves come with heavy requirements: storage, bandwidth, continuous operation. And so that's not really realistic for mobile wallets, for browser-based applications, for IoT devices, or even agents. They're also not always online. So full nodes solve the problem, but they don't really scale real usage. On the other side, we have light clients. They reduce the resource requirements, but they still need to synchronize. They still need to stay up to date. They still consume bandwidth, and if they're offline, they need to catch up before they can be trusted again. So again, technically correct, but not practical. And that leads us to an important conclusion. The ecosystem did not choose RPC by accident. It was forced into it because it's the only approach that is simple, fast, always available, even though it requires trust. So we didn't choose trust, we accepted it because the alternatives just didn't fit. So what happened in practice? Full nodes are too heavy, light clients are still too demanding. The ecosystem defaulted to RPCs, not because they're ideal, but because they work. RPC is simple. You just send a request and get an answer. It's fast. It's always available. It works on mobile. It works in the browser. It works everywhere. And most importantly, it requires no setup, no sync, no state, no waiting. RPC is amazing. Fast, simple, works everywhere, and completely unverifiable. Perfect product, terrible security model. Yeah, it's just that one thing. It requires trust, and that's the trade-off that we made. We optimized for usability and accepted that the data is not verified. RPC is not wrong. It's just incomplete. We optimized for UX and outsourced truth. So if full nodes are too heavy, and if light clients are still too demanding, what do we actually need? We need something different. Yeah, of course. We need a way to verify data without running a full node and without synchronizing the chain, without storing state. The application doesn't need a whole chain. It only needs answers to very specific questions. What's my balance? Did this transaction happen? What's the result of this contract call? So instead of syncing everything, we should be able to verify just an answer on demand and only when we need it. We need a primitive that allows applications to verify individual pieces of blockchain data independently, locally, and without prior contexts. No sync, no state, no trust, just verification. Verify only what you need, when you need it. And this is what stateless clients do. They implement this missing primitive. A stateless client does not store blockchain state. It does not synchronize with the network. It does not track the chain over time. Instead, it verifies on demand. When the application asks a question, the stateless client receives the answer and proofs, and then it verifies the proofs locally. So on your mobile device, within the browser, on your IoT device, or even the agent in its environment. Instead of syncing the whole blockchain, it verifies only what it needs, when it needs it. This is why it's called stateless. There's no persistent state, no continuous process, just request, proof, verification. No sync, no state, no trust. And this leads to a fundamental paradigm shift. Today, applications trust their data source. They ask an RPC endpoint and they assume the answer that they receive is correct. With stateless clients, this changes completely. The application no longer trusts the source. It verifies the result. That means it doesn't matter where the data comes from. You can fetch it from any RPC, from multiple RPCs. You can even fetch data from an attacker. It doesn't matter. That's the whole point, because correctness is no longer based on trust. It is based on proof. And these proof answer two questions. First, the question, is the data actually part of the block? That's the execution proof. And secondly, is this block valid and part of the canonical chain? That's the consensus proof. If both are valid, the data is correct. Not because we trust the provider of the data, but because we verified it ourselves. So that changes the role of the RPC. We still need RPCs, but the RPC then just becomes not a trusted authority like it is now, but merely a transport layer. And that's the key shift from trusting infrastructure to verifying results. The source becomes irrelevant, only the proof matters. And once you do this, you eliminate an entire class of attacks. Verification replaces belief. So what changes? First, security. All the attacks we discussed earlier, they stop working. If data is manipulated, the proof fails. If data is outdated, the consensus check fails. If a transaction is hidden, you can detect inconsistencies. If a simulation is altered, it no longer matches provable state. The application no longer trusts the input, it verifies it. But this also changes system design. This works in environments where full nodes and light clients don't. Mobile devices, browsers, IoT systems, AI agents. These systems don't need to stay online. They don't need to sync. They don't need to store anything. They can come online, verify what they need, and then continue. That opens something new. You can build systems that act on blockchain data without trusting infrastructure. This is especially important for autonomous systems because they don't have human intuition. They need guarantees, and stateless verification gives them those guarantees. Let's connect this to the Ethereum Foundation's direction. Recently, the EF formalized a set of core principles, CROPS: censorship resistance, open source, privacy, security. And these are not optional. They are non-negotiable. Well, then let's look at the access layer today in light of these core principles. Censorship resistance. Well, RPC providers, they can filter or block responses. Open source. Well, currently, users depend on infrastructure they don't control or verify. What about privacy? If all your reads go through a centralized endpoint, that exposes what users are doing. And security, the data is not verified. So the current access model violates CROPS on every level, and we all know it. And this is exactly why stateless verification fixes this. So with stateless verification, talking about censorship resistance, you can use any data source. Verification makes them interchangeably. Open source. Well, verification happens locally, transparently, on your device, in your environment. Privacy. You are no longer tied to a single observer. You can obfuscate what you want to do, or read your reads, not just what you actually want to write to the blockchain. And security, well, if every response is proven, then you can actually trust it. This is not just a technical improvement, it's a CROPS-aligned access layer. And if CROPS is the direction, then verification at the access layer becomes required. If the access layer is trusted, the system is not trustless. If we make the access layer trustless, then we're totally CROPS-aligned. And the shift is not theoretical. The Ethereum Foundation's Wallet SDK project, Kohaku, is moving exactly in this direction. Yesterday, there were a good number of talks about Kohaku, both here on the main event and also on other side events like the Stateless Summit. And the goal is simple: remove RPC trust from wallets, not the RPC data itself, but the trust in it. Instead of trusting infrastructure, the wallet verifies the data it receives. Stateless verification is being integrated as part of that architecture. And Colibri is part of this integration. What this means is wallets are starting to change how they access Ethereum from trusting RPC responses to verifying them locally. This is not something that might happen in the future. It's already entering real systems now. Wallets are moving away from RPC trust. And this is exactly what we built with Colibri. So this is what it looks like in practice. Colibri, and that's what we're building, is a fully stateless client. It verifies blockchain data locally. No sync, no stored state, no trust in RPC. When the application requests data, Colibri receives the answer together with proofs, and it verifies the execution that the data is part of the block and consensus that the block is valid and part of the canonical chain. And only then the data is accepted. The application does not change much. It still asks for data, but now every answer is verified before it is used. This works across environments, mobile devices, browsers, IoT systems, even very constrained hardware. And that's the key point. Verification is no longer something heavy. It becomes lightweight enough to run everywhere. What used to require a full node can now run on a phone. Verification moves to the edge, from infra to the device. And once you can do this, there's no reason to trust the data anymore. Now let's go back to where we started. Ethereum is trustless, but the way we exit it is not. We trust the data, and that creates a silent failure. Because if the input is wrong, everything built on top of it is wrong. We saw why this happens. Phone nodes don't scale. Light clients don't fit all environments. That's why the ecosystem defaulted to RPC. And RPC requires trust. Stateless clients changed it. They make verification lightweight, and they make it practical. They make it possible to verify data everywhere. And it aligns with the direction of Ethereum itself. Crops requires it. Wallets are moving toward it. It is already happening. Then the conclusion is simple. If your application cannot verify its inputs, it is not trustless. And once verification becomes possible, there's no reason to not use it. So don't trust, verify. Here you have some more information. You can check that out. You can see the white paper, the specification, and also the GitHub repository. I know the next person already waiting in line, so if you have any more questions, it's not just me. There's 2 more Colibros also there. And if there's anything that we want to discuss, we can take it outside, and then we can discuss everything in more detail. So thank you for stopping by. And remember, don't trust, verify.
Thanks a lot. You still have 2 minutes if you want to take one question.
Okay.
Thank you. If I'm interested in my Ethereum balance, just proving the corresponding account value is enough. So storage proofs are enough. But if my wallet want to have a look at my ERC20 balance, then this is a call. In JSON RPC we do a call. So it's not just about the storage being proven, but also about the EVM execution that extract that storage being proven. So how would stateless client do? Would we be able to prove the execution of the call, or would we prove all the storage and then rerun the EVM locally?
You mean like doing the simulation locally, or?
Yeah.
Yeah. So we also implemented right now just in a basic form, but we're still working on it to have a simulation locally. And for that, we first of all download the data, download the proofs for that, so that we can also run the simulation on verified data. And then we show the simulation results locally, and after that, you can then send out the transaction that you want to do.
Thanks a lot, Jork.
Okay, thank you.
And as you said, you have a full team here to answer all the questions. So please ask your questions if you have some.